Consider an axially loaded member with 10 kilonewtons applied 0.4 meters from one end and 0.6 meters from the other end, and fixed on both ends. We can draw a free body diagram and suppose that the reactions are opposite to the applied load. Let's call this B, C, and D. So this is the reaction at D and the reaction at B. And if we sum the forces in the x direction, we have 10 kilonewtons minus RB minus RD equals 0. And that's all statics can tell us. And so since we only have one equation and two unknowns, one equation, two unknowns, you may recall from statics, this is called statically indeterminate, get an R in there, indeterminate. And now that we can analyze forces and deflections, we have tools to solve these types of problems. And one tool is called the principle of superposition, which says that so long as the reaction to the loads are linear, as is the case with our situation, delta equals PL over AE, the deflection is linearly proportional to the load, then we can break up the problem into two smaller problems. We can suppose that it's fixed on one end and we apply our 10 kilonewtons and it's free on the other end. And we can add to that, so if we add these two scenarios together, we get the situation above. And so for this, we can calculate that the deflection caused by the 10 kilonewtons is going to be 10 kilonewtons, and it only acts on this part here, so 0.4 meters, and divide that by the area and the length. And then we have the reaction at D removes that deflection. So we have another deflection that will be the reaction at D, and that will act over the whole length divided by AE. And these two deflections have to be the same to get back to the case where there's no deflection at D. And so that means that 10 times 0.4 over AE equals RD times 1.0 over AE. And because A and E are constant for the entire thing, we can cancel them out, multiply both sides by AE, and we're left with RD equals 10 kilonewtons times 0.4 meters divided by 1.0 meters is 4 kilonewtons. So that's one way to do it, the principle of superposition. And a separate way to handle these is the compatibility equation, which says that if we have that labeled. It means that the deflection in part BC plus the deflection in part CD has to add up to 0. And we can look at, for example, if we put a cut through here, we would see this is the force in section BC, and this is the reaction at B. And if we put a coordinate system on here and we sum the forces in the x direction, we see that PBC minus RB equals 0. So the force in section BC equals the reaction at B. So then we write that the reaction at B times the length for force BC, which is 0.4, over AE, and the deflection CD is going to be shrinking, so minus the reaction at D times 0.6 over AE equals 0. And again, these cancel in this problem, and we get that the reaction at B equals, that's fine. The reaction at D, 0.6 over 0.4. And we already have this equation. And so when we combine those, we get, for example, that the reaction at D times 0.6 over 0.4 plus RD equals 10 kilonewtons. And so the reaction at D equals 10 kilonewtons over 0.6, 0.4 plus 1 equals 4 kilonewtons. The same result we got with the principle of superposition.